In this video, we will discuss a new optimization algorithm, that is Capuchin Search Algorithm. This algorithm is basically inspired by the Capuchin activities, their food search behavior, and different strategies they use for the survival in the real life. All these are simulated in this algorithm to find out the optimal solution to the different optimization problems. So this algorithm is introduced in 2020, and the main inspiration behind this algorithm is the behavior of Capuchin monkeys. And this algorithm performance is also tested on 23 different benchmark test functions, and it is also applied to solve several engineering design optimization problems. And when the algorithm performance is compared with other algorithms, this algorithm provides efficient results with higher convergence rate. So we can use this algorithm to solve a number of optimization problems and also real life optimization problems. So as this algorithm is inspired by the Capuchin behavior, their activities and different strategies they use for the survival in real life. So first we will discuss few facts about Capuchin, their behavior and other, so that we can easily understand how the algorithm is working. So they prefer to live in dense and humid forest where they can use variety of food sources, shelter. So they can easily found in countries like Brazil, Peru, Costa Rica, Argentina, and in the Central America. They live in groups, and the group size, it depends upon their species. It is 10 to 30 individual, and it also depends according to their species. They have different group size. About lifespan, they can live 50 to 25 years in wild and longer in the captivity. And about their diet, you can see they use both plant-based and animal-based food. Like plant-based, we have fruits, leaves, flower, nectar, nuts, birds, and rather than this, they can eat insects, spider, lizards, frog, birds. About their habitat, you can see they prefer to live in dry forest, rainforest, and the secondary forest. So about communication, they are vocal animals. They use variety of different sounds to communicate with each other. They use different bark, whistle, and screams to communicate with each other. And they also use different facial expressions and body language. So everyone has their different sounds. By that, other members can recognize them. Next, you can see here the leader. They live in groups and they follow leader. So they often follow a selected leader as they make their way through the forest in a single line by following their leader. A leader is responsible for identifying the food sources for the group members. Follow the leader in a line when they go for the food search. And they are highly intelligent, and they are also used in the research subjects in studies of monkey behavior and neuroscience because of their intelligent skills. So they are active during daytime, and the food search is an important part of their daily routine. During food foraging, they can search alone or with other species. So they are highly intelligent, and their intelligence helps them to solve problems, and they create way to gather food sources. And they also use tools to crack nuts and use their sharp senses in discovering food sources. So about tools, they know how to use sticks, stones, leaves to extract food and open nuts. Search food in groups, and each group cover large area in the forest, and each group search for the best areas within the forest that contain maximum food sources. And the group is often led by Alpha Capuchin, that is the leader. So the group leader is responsible for locating food sources to each member of the group. And in case when there is not enough food found in any area, the group splits into smaller subgroups and find food independently. All these behaviors are simulated in this algorithm that step by step we will discuss in the upcoming slides. Next, you can see here their movements. They use different movements. So Capuchins are also known for their 3-meter leaps that they often use to go from one tree to other over ground from one river bank to the other. So here you can see during food search on trees, river banks, ground, Capuchin used their 3 excellent skills, that is jumping, or we can say leaping, swinging, climbing. So in this algorithm we have followers and leader. So both follower and leader will continuously improve their strategies till the point at which a food source is found. So here in this algorithm all these movements are simulated, like leap on trees, leap over river banks, walk on ground, swing over tree branches, move naturally and randomly. Next you can see the strategies they use. So in real life they use different strategies for their survival. So here we have 3 strategies they are followed in this algorithm by the leader and the follower during food search. So first strategy we have follow leader, that is the alpha male. So the group is led by alpha, or we can say that is the global leader. So this leader is responsible for identifying the food sources for all members in the group, and all members will follow the leader in order to obtain their food. Next strategy we have follow both male and the female alpha, that is the group leaders. So in certain Capuchin species the group members follow both male and the female alpha leaders. They are the global leaders who are in charge of group, and they are also responsible for identifying the food sources and accordingly guide the other members of the group to other food sources. Third we have independent search. In case when there is no enough food in any area, then the group will further divide it into subgroups and they seek for the food sources individually, independently, that is independent search on their own, but they follow group member who find food sources. Here we have 3 different strategies they are followed in this algorithm and different movements. Here you can see we have different steps, and here you can see all the movements are followed here: leap on trees, leap over river bank, walk on ground, swing on the tree branches, climb on the tree, relocate randomly. So all these movements are simulated in this algorithm to find out the optimal solution. So here you can see different steps are used in this algorithm. First we will generate a random number between 0 and 1 that is used further in this algorithm. Then we have a constant value 0.5 that is also used here for the comparison. You can see here p value is used here, 0.5 for comparison. Then we will initialize the population for n Capuchin. After that use the objective function and calculate the fitness value for each member. Then we will initialize the velocity for each Capuchin, randomly select some Capuchin and the number should be less than total population divided by 2. After that start the main loop, update the parameter. Then for all Capuchin we will update the leader velocity. Then we will use different movements to update leader position: leap on trees, leap over river banks, walk on ground, swing on the trees, swing on tree branches, climb on tree, relocate randomly, else we will update the follower positions. If the condition is not true, then update the follower's position, and then in the end calculate the fitness value for the new solutions and the loop. Check the stopping criteria. When this stopping condition is met, we'll stop and display the best solution that you found in the last iteration. Now step by step we will try to understand the working of this algorithm. First we need a random number that is between 0 and 1. So here you can see the example of random number between 0 and 1. First we have 0.1259 or 0.3650, 0.1045. You can use any random number here that is uniformly distributed between 0 and 1. Then we need a constant value for the p, 0.5, that is used in if-else statement. Next we will initialize the population for the n Capuchin in the search space randomly. So here we are using this equation to initialize the population for each member. Suppose we have the population size, that is the total number of search agents, or we can say the total number of Capuchin 3. Here you can see we have population size, that is 3. We have 3 members. Then we have dimension 2, 1 and 2. Here you can use any number of search agents, 50, 100, 1000, it depends. According to your optimization problem, you can use the number of design variable, that is dimension D. For example, we are using here just 2 dimension. So here now we are using the bounds, that is the search space boundary. Lower bound we have -100, upper bound we have 100. So in this algorithm we are consider the forest as the search space, and search agents we have the Capuchins. So initialize the position for each member using this equation, upper bound plus a random number that is uniformly distributed between 0 and 1 into upper bound minus lower bound. Next you can see here, suppose we will find out, suppose here you can see we calculated the position for the first agent for 2 dimension. So here we have upper bound 100, we have any random number, suppose we have random number 0.2315, and we will do this for 2 dimension. Here we have 1 for 1 dimension, here we obtain the value. Then for the second dimension, you can see the j value is 2 here, j value is 1 here. Put the value here, upper bound we have 100, lower bound we have -100. Suppose the random number for when j is 1 is this one, then j is 2, the random number 0.1603, and we got the value here 146.3 for first dimension, 132.06 for the second dimension. Like that we will find out the value for second and third search agent for both dimension 1 and 2. After that we'll apply the objective function here to find out the fitness value for each Capuchin. So here you can apply here objective function on the position. Suppose we find out the initial position for second and third also. Now apply the objective function on the initial position and then find out the fitness value for your search agents. After that we will initialize the velocity for each Capuchin. Suppose it is 0.1 into their position. For the first agent you can see we have the position for first dimension we have 146.3, so 0.1 into this. Then for the second dimension, for each agent we will calculate the velocity for each dimension. Done. Like that we'll calculate for each Capuchin. So we have their current position, then we have their current velocity, that is the initial position and the initial velocity. Now here when we will select the Capuchin, the number of selected Capuchins should be less than n by 2. N is the population size divided by 2. This we are using to represent the leader and the other remaining Capuchin, that is the followers who follow the leader. So in the group we have follower and the leaders. So we use selecting the, so now we are selecting just some Capuchin from this. So suppose we have population size 100. So 100 divided by 2, that is 50. So we selected only 50 Capuchins randomly. Now we start the main loop here. Check whether the current iteration, that is k, small k, it is less than or equal to maximum iteration, that is capital K. Repeat the loop until. Then we will update this parameter. We are using this parameter here to represent the lifetime of the Capuchin. So in real life it is quite natural, but here we have the virtual environment, virtual Capuchins, virtual search space, that is the forest. So we have the virtual lifetime for the Capuchins that we will calculate using this. This function will also maintain the balance between the exploration and the exploitation phases during the global and the local search. And here the value for beta naught we have 2, beta 1 21, and beta 2 is 2. They are used in this algorithm. So these parameter values are used here in this algorithm. So we will start the loop here. Now for all Capuchins, here we have nested if statement. So first we will check the value for k, whether it is less than n by 2, that is the randomly selected Capuchin. If this condition is true, then we will go inside this loop, else we will update follower position. Again, here you can see if this condition is true, then we will update leader velocity, leader position. For the leader position, again we have different movements: leap on tree, leap over river banks, walk on ground, swing over branches, move naturally, randomly. So if this condition is true, then we will move the leader, and we will move the leader according to different movements. Else we will update the position for the followers. After that, calculate the fitness value. So the first step here we have, suppose this condition is true, we will now go inside this loop. Here we will update the leader velocity using this equation. Here for more details you can read the main research paper, where for the velocity calculation they explain in detail like how they calculated the initial velocity, how they calculated the horizontal velocity, vertical displacement and other. So right now the final velocity for the leader is calculated using this equation. So rho, that is the inertia coefficient, and value used for this we have 0.7. and here you can see this is the current velocity for the Capuchin, for the leader. And here this is the, here you can see A1, A2, they are the positive constant with value 1. And here you can see x best, this is the best position among all, and here this is the current position of the current individual. And here R1, R2, they are the random numbers normally distributed between 0 and 1. And here Fj, that is the food source position. So here using this equation we will update the velocity for the leader. So when the velocity for the leader is updated, now we can update leader position. So here you can see leap motion of the Capuchin, then they can leap from tree branches to other branches, on river banks, over river banks, ground and other. After that we will go inside this loop, we will use any random number between 0 and 1, compare the value here. If this condition is true, go inside this loop, then p value we initially define, to compare with this. If this condition is true, then go inside again. If this condition is true, then compare with 0.2. If this condition is true, then we will update the leader position according to the leap on trees. So different movements, again I'm saying here, leap on trees, leap over river banks, walk on ground, swing over branches, move naturally and randomly. So we have if-else statements, that is nested if statements. Accordingly we will perform the leader movement. So first you can see here, if this condition is true, then update leap on tree, else update leap over river banks, else update walk on ground. If none, else, now here you can see else swing on the tree branches, else climb on the tree, and else relocate randomly, else, and if none, else we have the second case, update the follower position. So first we have leap on the tree. So how we can update the position for the leap on tree using this equation. Here you can see this is the food source Fj. You can see the simple equation is used to represent the leader position according to leap on tree. Here this is the food source, plus we have this balance provide. So this parameter used to provide this parameter is used here for balance provided by the Capuchin tail. So here they are using their tails to grasp on the tree branches to find food sources on the other side of the branch. So using this factor, we're using here this. Then this is the velocity that we calculated for the leader. Then we have a jumping angle, that is 3/2 theta, that is 3/2. So sine 2 theta, and the theta value we're using here 3/2. G is here the gravitational force, and the constant value for this used here 9.81. And here we're using when value for I is less than total population divided by 2. And here this is a random number between 0 and 1. After that, as this condition is true, then here we will update the leader position according to leap over river banks. So here we are using this equation. Here this is the elasticity probability of the Capuchin movements, PEF. Here you can see this is PBF, that is the balance provided by the tail, and here this is the elasticity probability of the Capuchin movement. Then sine 2 theta, the jumping angle, gravitational force, and all are same values. After that, else we will update the leader position, walk on the ground, using this equation. So walk on the ground is simple, random, natural. So in the current position we will add the velocity that we calculated. So walk on the ground is simple. In the initial position we will calculate the velocity that we calculated, like we done in particles form optimization. When we want to update the particles position in the initial position, update the calculated velocity. So this is same here. Here you can see after next, else this condition is true, then we will update the leader position according to swing on tree. Swing on tree branches. Here you can see the explanation for this. So in this case, if some alpha Capuchin and other Capuchin may use local search to search food on tree branches and all tips of the tree branches, so by wandering over the smallest distance. So they use their tails to grasp the tree branches and use swing operation. That is, here they use this operation. Here you can see weight, that is mg, mass into the gravitational force. Here it is mg sine theta, mg cos theta. For more detail you can check the research paper. Everything they did explain in detail. Here you can use this equation to perform this operation for the swing on the tree branches. Here Fj, that is the food source. This is the PBF, we already explained here. This is the balance provided by the Capuchin tail. Next we have sine 2 theta. Theta value is theta is equal to 3/2. Else if this condition is true, then update the leader position according to climb on tree. Here you can see during food search, alpha, that is the leader, and the other Capuchin, they also climb on the trees to search food. So here you can see this is the Capuchin and here we have the branch. So using this equation we can update the leader position that is used to represent the climb on tree. Here we are using its velocity minus previous velocity. Else we will update the leader position randomly. It means it will relocate randomly. Here we are using, this is a random number, done, and lower bound, upper bound, will locate randomly using this. If finally above case is not true, then the next case we have update the follower position. You can see the equation that we can use to update the follower position. 1/2. Here we have the leader current position, and here this is the follower current position. According to this we can update the follower position. After that we will calculate the fitness value for new search agents. When the new solutions are found, we will compare them with the older one, and after comparison we will keep the best one and replace the worst solution. After that we will check the stopping criteria. If the stopping condition is met, then for all search agents, then among all search agents, suppose we have 1 to 100, we will display the best among all, having the best solution. If you are doing the minimization, consider the minimum value as the best, and if you are doing the maximization, consider the maximum value as the best value. So again I want to repeat the loop here. Here you can see for all individuals we are using here from 1 to population size. We are not updating the position for just one individual. Suppose we have 100 individuals, then here update for all 1 to 100. If this condition is true, then update leader position, leader velocity, else we will update the follower position. And when the leader position is true, then again further we will go, then again we will check whether the this condition is true or this one. Then again we will check if this condition is true, then we'll go inside this loop, and here we will check if this condition is true, then go inside this loop, else this, else if this. So here for all the movements here we are given. So we will select the one and accordingly update the leader position. So that's all about this video. If you have any question, you can comment below, and thanks for watching this video.